Cerebras Systems was founded in 2016 in Silicon Valley by Andrew Feldman, Gary Lauterbach, Michael James, Sean Lai, and David Patterson with a bold idea. The biggest limitation in artificial intelligence hardware was not raw compute power, but the way chips were being built and connected. At the time, the AI industry was already heavily shaped by NVIDIA, whose GPUs had become the standard for training deep learning models. NVIDIA's approach relied on scaling by connecting many relatively small chips across servers and clusters. This worked well early on, but as AI models, especially transformer-based systems, grew into hundreds of billions and then trillions of parameters, the weaknesses of distributed GPU computing became more visible. Training required constant communication between GPUs, which created bottlenecks in bandwidth, synchronization delays, and increasing system complexity. Cerebras focused on a different core problem: data movement. In large AI training workloads, moving data between chips can become more expensive in time and energy than the computation itself. Instead of improving interconnects between GPUs, Cerebras asked a more radical question: what if there were no inter-chip communication at all? This led to its defining innovation: wafer-scale computing. Rather than cutting a silicon wafer into many separate chips, Cerebras uses the entire wafer as a single processor. This produces the wafer-scale engine, WSE, a chip that spans an entire wafer and contains hundreds of thousands of compute cores connected through a high-bandwidth on-chip network. This design fundamentally changes how AI systems operate. In traditional GPU clusters, workloads are split across multiple chips, and performance depends heavily on how efficiently those chips communicate. In Cerebras' approach, most of the computation stays on a single wafer, dramatically reducing the need for external communication. This can simplify software design, reduce latency, and improve performance consistency for large-scale AI training tasks. Cerebras builds complete systems around this chip, integrating compute, memory, and networking into a unified AI appliance designed specifically for deep learning workloads, particularly large transformer models. However, wafer-scale computing comes with significant engineering challenges. Manufacturing such a large chip is extremely difficult because even small defects on a silicon wafer can normally ruin an entire chip. Cerebras solves this by designing redundancy into the wafer-scale engine, allowing faulty sections of the wafer to be isolated so the rest of the chip can continue functioning. Even with these innovations, wafer-scale production remains complex and expensive compared to conventional chip manufacturing. The company's strategy is not to compete with GPUs on every front, but to target a specific bottleneck: large-scale AI training efficiency. While GPU clusters scale horizontally by adding more chips and networking infrastructure, Cerebras scales vertically by increasing the size of a single compute unit. This difference in philosophy leads to two very different computing models. NVIDIA's model is flexible and widely applicable across AI training, inference, graphics, simulation, and cloud computing. Cerebras' model is more specialized, focusing primarily on training large neural networks where communication overhead is a major constraint. Despite its technological innovation, Cerebras faces a difficult market reality. NVIDIA's dominance is reinforced not just by hardware performance, but by its software ecosystem, especially CUDA, which is deeply embedded in AI development workflows across industry and academia. This makes switching to alternative architectures costly and complex. As a result, Cerebras has positioned itself less as a direct replacement and more as a complementary solution for specific high-end workloads where traditional GPU clusters become inefficient. Over time, Cerebras has refined its role in the AI landscape. Rather than trying to replace GPUs entirely, it focuses on proving that wafer-scale integration can solve real problems in large model training. Its systems aim to reduce training time, simplify distributed computing challenges, and improve efficiency for frontier-scale AI research. The story of Cerebras is ultimately about challenging a fundamental assumption in computing, that smaller chips connected together are always the best way to scale performance. By reversing that assumption and betting on a single massive wafer-scale processor, Cerebras has pushed the boundaries of semiconductor design and forced the industry to reconsider how AI hardware should evolve. Even if it does not displace NVIDIA's dominance, it has already influenced how engineers think about scaling limits, communication bottlenecks, and the future architecture of artificial intelligence systems.